Before I move on to the next example, I want to answer the first two questions that I raised in the very beginning of this week. The first question is there a quick way to check whether a vector field is a gradient vector field? Firstly, now we have a better question to ask. Instead of whether it's a gradient vector field, is whether it's conservative on a region D. Okay? Then, as we discussed earlier, that really depends on the shape of D. In particular, the first question that you should ask is D simply connected? So in other words, whether D has any hole. So for example, if D is simply connected, then, well, your life is very easy. So you only need to check whether Qx minus Py equals 0 or not. Okay? So when you have a simply connected region, then determining conservative field or not is super easy. However, in the case when your region has holes, so when it's not simply connected, then, I'm sorry, the only way to check whether it's conservative or not is to check whether line integral along C equals 0 or not for F3 simple closed curve C. Okay, so you need to check. So check this. Okay, so if you discover one of the such line integral is not 0, then you conclude that it's not conservative. The other question was, is there any easy way to compute line integral for a general vector field? The answer is, okay, previously I say Green's theorem. Now we have an even better answer, that is the generalized Green's theorem. Okay? So this really summarizes what we have done this week. Now we come to the last example of this week. I hope this will help to summarize everything that we have done this week. This is a very important example. Let's put a star here. And also, I've made some very similar questions in homework 10, question 3, and question 4. Please attempt this yourself and try to see if you manage them. If you manage this, that means that you really understand the materials of this week. Okay, consider the vector field. Yes, the same vector field that you have seen 100 times. In particular, you know that P and Q, if I call this P and Q as usual, P and Q are continuously differentiable, C1, on the entire R2 except the origin. Because at the origin, the denominator explodes. Okay? So part 1, evaluate the line integral of f dr where C is any simple closed curve that does not enclose the origin. So what does that mean? So you have the origin in the middle, and then what is C? C is any simple closed curve that is away from the origin. Okay? So in particular, this simple closed curve will bound a region, which I call it D. Okay? So since C does not enclose the origin, so that means that the region D does not contain the origin. With this really tautology, it means that it's really the same thing spoken in different way. Okay, so but the key thing is then. So in particular, that means that P and Q, because it does not contain the origin, so P and Q are C1 on D. So therefore, you can apply Green's theorem. Okay, you can apply the usual Green's theorem that the line integral f dr by the usual Green's theorem. To apply this, you need to make sure that P and Q are C1 on the region D, which is the case here. So this equal to the double integral of Qx minus Py dA. But then we have seen in example 4 that, so we have checked in example 4 that Qx minus Py equals 0. Then of course integrating 0 surprisingly is 0, so we're done. Okay, this is the answer. So when your curve does not enclose the origin, then you apply the usual Green's theorem. The more tricky part is the next one. Evaluate the line integral, the same thing, for any C simple closed curve that encloses the origin. So what does that mean? So now the origin is in the middle. Okay, and then you have simple closed curve. You don't know how it looks like. It looks like this. Okay, and then it encloses the origin. So now the usual Green's theorem does not apply. How do we do with that? Is at the end? Not quite. The idea is let me use a different letter, C epsilon be a circle with circular path small enough to be fitted inside the region bounded by C. So what does it mean? That means that, okay, let me choose a path, a circular path, a circle, small enough such that it fit into the region bounded by C. Okay, so look like this. And then these two curves, now I have two curves, C and C epsilon, they will bound a region. Let me call it D. Okay. Then you have two or more than one simple closed curve, so you don't use the usual Green's theorem, but the generalized Green's theorem. Then by the generalized Green's theorem, okay, the double integral of the Qx minus Py dA equals to the line integral of the outer boundary, so outer boundary is C of f dr minus the integral of the inner boundary, which is C1, C epsilon f dr. Okay, and then the good news is D is 0, so the whole thing becomes 0. Therefore, we have this guy minus this guy is 0. That means that they're equal. So therefore, the line integral of C f dr equals to the line integral of C epsilon f dr. But then we have seen from, well, the computation last week. So if you use a direct computation, because now C epsilon is a circle, it's not a random curve, so you know how to parameterize that. So C, example 8 from week 9. Okay, if you see, look at this, we actually have done this computation. The answer is 2 pi. But this is very fascinating. Okay, if you look at the result, it's very fascinating. What do we prove? We prove that the line integral of any simple closed curve, as long as it encloses the origin, as long as the region bounded by it contains the origin, then it will equal 2 pi. It does not matter how the shape of C is, no matter how it looks like, as long as it's bound the origin, then it equals to 2 pi. So this addressed the mystery of last week. Okay, so at the end I decided to open the notes from last week. Last week we have a mystery of, okay, why does this integral always equal to 2 pi alpha? It does not matter how big the circle is, because no matter how big the circle is, it encloses the origin. So the answer would be 2 pi. Okay, of course 2 pi alpha because I have alpha here, but if alpha is 1, then this is 2 pi. So it does not matter how big or how small your circle is. We actually did something even better. It does not matter how the shape of your simple cos curve is. As long as it encloses the origin, the answer would be 2 pi. Okay? So far, all the line integrals that we deal with are simple. Simple in the sense that all the loops that we deal with does not intersect with itself, okay? But what if I have a non-simple curve? Is it the end of the world? The next part tells you that it's not. Part 3. Evaluate the line integral f over c, where c is a super fancy curve here. In particular, here you have a self-intersection, so this is a non-simple curve. But as I say, when you deal with non-simple curve, that's not the end of the world. The idea when you deal with non-simple curve is to decompose C into simple curves. Or let me say pieces of simple curves. Pieces. Okay? What does that mean? If you look closely about this curve C, it really can be decomposed as, firstly, you have this, and then secondly, you have this. Okay? So, if I write down, so this is really the guy outside. Sorry for my drawing, I hope it makes sense. C1. And then also, there's another guy, another loop inside. Okay, C2. So it really is C1 plus C2, if you think about it. Okay? But now, the good news is C1 and C2 are simple curve because there's no self-intersection. So, in the line integral of C, f, dr equals to C1, the line integral, f dot dr, plus the line integral C2, f dot dr. Okay? But then now, where is the origin? The origin is here. So that means that, okay, the origin is here and here, respectively. So in particular, as both C1 and C2 encloses the origin, using part B, I know that the line integral of C1 f dot dr and the line integral of C2 f dot dr, they both equal to 2 pi. Because as long as your curve is a simple cos curve that encloses the origin, then the previous part tell me that the line integral will equals to 2 pi. Sorry, not part B, part 2. Okay, using part 2, you will have this. So hence, the total line integral in this case equals to 2 pi plus 2 pi, which is 4 pi. Okay, that's the answer. So finally, I give you a question for you to think about. Okay, if you really understand this example, then it shouldn't be too hard. Can you give me an example of C, of a cos curve C, not necessarily simple, such that the line integral is 6 pi? Okay, so here I give you an example that a line integral can equal to 4 pi. Can you give me an example for which the line integral equal to 6 pi? So I let you think about it. Okay, so let me know if you do not understand this question, and then email me if you have any confusion.